Almost settled. Great. It's my pleasure to introduce Raymond Ehlers. Raymond received his BA in physics from Columbia University and a PhD from Yale University. He held postdoctoral positions at Oak Ridge and Lawrence Berkeley National Labs, expanding his work to include statistical inference methods with the Jetscape collaboration and studies for the electron ion collider with the ECCE proto collaboration. He is currently a convener of the Alice Jet and Hard Photon Physics Working Group and recently completed a 4-year term leading the Jetscape Working Group on Bayesian inference for jet quenching. His research focuses on QCD matter under extreme conditions, using jet substructure and theoretical comparisons to characterize the quark-gluon plasma. And today he's going to be talking about what can jets reveal about microscopic structure of QCD matter. So without further ado, I think you can take it away.
Excellent. Thank you very much. Good afternoon, everyone. I apologize. My voice is a little gravelly today. I started losing it yesterday. Seems to be hanging in for now, but if anything is unclear, please let me know. Yeah, thank you for the opportunity to speak here again this week. So I wanted to build up on what we discussed last week, and I was just going to do a brief recap, given that in case anyone wasn't anyone wasn't able to attend last week, or otherwise just to kind of remind us, get us in the flow of what we want to discuss. So we talked about QCD matter, or QCD. We had then added matter to the equation through our heavy ion collisions, and then talked about the dynamics of jet quenching, all from a little bit of an experimental perspective. So I will continue this experimental perspective today and flash just a few slides to get us going here. So in terms of what we're starting, right, this is all about QCD, right? So this is the field theory of our strong nuclear force. And to be very explicit, this means that we're looking inside of our atom, inside of our nucleus, then into the constituent particles that are making up our proton, namely our quarks and gluons. And as we discussed, what's particularly of one of the many interesting features here is that gluons, our force carriers, are carrying color charge themselves, which leads to self-interactions that gives QCD its complex structure. So I again show these QCD vertices on the bottom right here, and yeah, all of this kind of builds to this rich complex structure that we'll be discussing today. So now, in terms of how to ground this discussion a little bit, what can we expect? I show these lattice QCD calculations at 0 barochemical potential, and here we plot this energy density properly normalized so that it's proportional to our number of degrees of freedom, where we see this expected phase transition. And what it really tells us is that we are transitioning from our hadronic to our partonic degrees of freedom, right? So moving from my measurable hadrons to the degrees of freedom associated with my quarks and gluons that I can't directly observe otherwise. But if we go to the high temperature behavior here, we still see the substantial gap between our non-interacting limit. Sorry, I should have gone full screen with this. Hopefully that's still work. Between our non-interacting limit on the right from the Stefan Boltzmann and where these calculations actually predict. So really, this difference right here is some complex set of bound states of quarks and gluons that really encode these interesting dynamics that we'd like to explore through our understanding, through our quark-gluon, through the quark-gluon plasma and our interactions with heavy ion collisions. Right, so these heavy ion collisions give us this opportunity to recreate the conditions of the Big Bang, or after the Big Bang, experimentally, and really gives us an opportunity to experimentally access these regions of the QCD phase diagram that we could not otherwise. So it's giving us an opportunity to look at something in the lab that is quite extreme in terms of, for example, our time scale, our energy density, our temperature, many different quantities you could use to characterize this. So as a brief reminder, the idea here is with these heavy ion collisions, we take nuclei and accelerate them to nearly the speed of light, and in doing so, we end up with an initial state where the nuclei are heavily Lorentz contracted. They have some initial set of interactions coming out of the initial state of the collisions, which then evolves into the quark-gluon plasma, which we tend to describe through a hydrodynamic evolution, but also have responses to external probes, we'll get to in a moment, that then hadronizes into these particles that we then measure in our detector. So there's this, what I particularly like about this diagram is it really highlights the multi-stage aspect of these collisions, which we'll in fact take advantage of when we talk about our statistical methods to disentangle what's actually going on in these interactions. Now, we've said jets at least a few times, so let's make it very explicit. What I will be talking about today is using these jets, these internally generated probes. So as I have my collisions of my nuclei, in rare cases, I will have a high momentum transfer interaction between two of my incoming partons, which will then lead to a self-generated probe of the quark-gluon plasma. We're really very fortunate that these exist because given these extreme scales, it would be, there really is no other way we have to externally probe these collisions. The time scales just don't work out when we're talking about scales on the order of 10 Fermi. And so I will be discussing today how we can use these jets to probe these dynamics and understand the details of the structure of the quark-gluon plasma as it evolves in these collisions. So to say just a little bit more to remind us about jets of the QGP, right? As I've said, we have these jets which are produced early. So I have collisions between my partons and my incoming nuclei that are going to form early, evolve with and interact with the medium. So you have these complex set of dynamics as I have my ingoing partons go out and interact with my medium. And you're going to have all kinds of sets of interactions here between my parton and the medium, which we tend to describe in terms of collisional and radiative energy loss. But collectively, these interactions between the parton and the medium are described as jet quenching. And so on top of these medium-induced interactions, you of course also have your regular vacuum-induced processes. Now, why are we interested in this? As I said, it's useful as a probe, but in particular, these are going to be high momentum interactions that we'll be most interested in, which through, for example, uncertainty principal arguments tells us that we'll be able to resolve shorter distance scales, which may give us an opportunity to actually resolve or probe and hopefully resolve the microscopic structure of the quark-gluon plasma. So not just kind of bulk properties, but really peering into how the medium looks at a small length scale. So in terms of the physics that we're actually going to try and probe here, there's kind of two perspectives. One we can take is from the probe of the medium. So I have this cartoon from Jing where we have our parton propagating through our medium. And as I said, you have these collisional and radiative terms. So I can ask kind of questions about what does my parton resolve? Can it actually see this internal structure of my medium? I can also turn this question around and ask, what does my medium resolve in the jet shower? Can it be seen if I have a splitting in my propagating parton? Can the medium actually resolve this difference in the splitting? We'll talk about this more experimentally in a moment. And then there's also a kind of a more complicated set of dynamics, namely asking how does the presence of one impact the presence of the other? So first we can think about in terms of how does the medium actually being there affect the probe? So this can be in terms of things like dependence on the quark flavor, other, for heavy enough quarks, this could be in terms of, for example, thermalization or dissipation into the medium. So there's really kind of some higher order effects you can imagine. I can also turn this around, and as I have my parton propagate, we can think of, for example, much as a duck moving through a pond can create a wake. You can think of the same sort of concept, but in terms of our momentum space dynamics. And we expect to see both, kind kind of correlated emissions in the direction of our hard parton, but also depletions going in this other direction. So can we actually resolve these structures? Now, I won't even be able to kind of discuss the physics in terms of this for some of these for the sake of time, but just to highlight what this means then in terms of kind of how we want to relate these, we want to relate these concepts to our actual experimentally observable consequences, of which I'll focus on three. So one is this concept of energy redistribution. So as I have my parton propagate in this direction through the medium, collectively, this set of interactions will cause emissions of energy to larger angles, which we will describe broadly as an energy redistribution term. We also can think about this in terms of modified structures. So again, my interactions between my medium and my jet are going to change what my jet looks like in my medium as compared to my reference in proton-proton collisions. And then we can also think of if I really scatter off some particular structure in my medium, this may lead to kind of overall jet deflection of the direction of my jet. And so what we will do is we will look for these experimentally observable consequences and try and map them onto the physics that I just described. So okay, maybe I'll pause for here in a moment, since this is kind of where I want to stop my recap. If there are any questions now, please raise them. Otherwise, as I go through, please feel free to raise your hand, and I am very happy to treat this as a discussion. So, okay, with all that being said, the two things that I want to try and focus on today are twofold. One being focusing on experimental probes, the core flow and plasma. So I'm going to highlight a few key jet quenching measurements, again, just to get us going, and then to focus in on jet substructure and how we can use that to probe the microscopic structure of the medium. And then I'm going to shift direction a little bit and talk about putting together a overall physical picture of these interactions. So how do we take these measurements that I've shown and actually put together a consistent picture where we're learning about these structure and dynamics of the medium through Bayesian inference. So okay, without further ado, then, so I'll focus first on this energy redistribution, and I want to define these terms because this is what we'll be thinking about throughout the entire talk. Namely, how do we characterize these medium-induced modifications of hard probes as they interact with our medium? And so, if you just think of it as a counting experiment, I'm going to record my collisions. And for whatever object I identify, we can first think just in terms of single particles. I'm going to record how many I get as a function, for example, of the transverse momentum, or PT, both in AA collisions as well as PP collisions. Now, if I want to construct an appropriate reference, there's some thickness to my nuclei. There's going to be multiple sets of interactions as they collide, and so I need to have some sort of geometric factor to account for this difference in my nuclei. But if I scale my proton-proton appropriately, I can construct we by conventions to construct this factor, the RAA, sometimes known as the nuclear modification factor, which evaluates at fixed momentum and is some sort of measure of possible yield suppression. So it's going to be what we measure in AA over PP normalized by these geometric factor. So what does this mean in terms of the plots we actually look at? You'll see something like this figure quite consistently. So some function of the RAA, where if I have no jet medium interactions, the expectation is due to this geometric factor that I will be my probes will be unmodified and the curve will sit at unity. However, if I see, for example, some sort of suppression in this curve, this will be some indication of energy loss, which we then can disentangle further. So okay, so we can start with just looking at inclusive hadron yield of yields measured in PP and AA, which is to say I'm going to take this event display, which I've shown a number of times today and yesterday, excuse me, last week as well. And I'm just going to count every particle as a function of momentum. Now, this figure is very busy, so let me guide your eye through it, but it's very useful because it is a nice compilation of a variety of measurements that are both sensitive and not sensitive to interactions with the medium. So if we start with this red and purple figures from measurements from at least in CMS, we can see kind of this characteristic shape of this RAA. This low PT region is what I broadly describe as non-jet physics. We won't focus so much on this, but what I want you to focus on is this characteristic slowly rising shape as we go to higher transverse momentum. And this is showing exactly in the case of inclusive hadrons, right? We expect these to interact through the strong force, which means that right, they're carrying color charge. And we see in the cases where they're carrying this color, a significant interaction. This is significant suppression. So the suppression is precisely telling us that we are having these energy loss effects that I just mentioned. Now, how do we actually validate that picture, though? We can do so by either looking at systems where we don't expect to have this formation as medium, at least in, okay, let's say the minimum bias inclusive case. So we can look at proton lead, for example. We see this is consistent with unity, or we can also look at probes that do not carry color charge, for example, our photons or WZ bosons. And we see all these are consistent with unity. So this is telling us that that we can put together a consistent picture in terms of our overall dynamics. And even at just the level of counting single particles, I can already say, right, that I have these interactions with my medium. It's one of the key pieces of evidence of the formation of the quark-gluon plasma. So let's add another level of sophistication, though. Let's get to these jets, which is, as you'll remember, are basically it is a way that we have constructed to try and get closer access to our partons, right? As they shower, if I measure just a single particle, I'm going to be losing some of the dynamics of my initial kind of 2-to-2 type scattering. So we construct this through this algorithm, this jet finding algorithm, a approximately cone. You can think of this conceptually, it's a little bit more complicated, but at least, or let's say the implementation is a little bit more complicated, but conceptually we can think of it as approximately this cone, this aperture in our phase space, our angular phase space, which we'll describe as a function of R, and we can play the same game in terms of constructing our RIA. So here I've shown a measurement from Elise, where there's a few things going on here. One, we see significant suppression. You look at the scale, it's about the same, although you have to be careful because our scale is going to be shifted compared to our hadron, for example, from the previous slide. So what we see here, nonetheless, is that we have significant yield suppression, but also that this background question that I highlighted at the end of last week is quite a significant impediment in terms of it will restrict the minimum momentum range that I can measure. Now, I was involved with a few collaborators at Elise, applying a novel machine learning-based background subtraction method, which allowed us to extend the range at which we could measure this down to lower PT, as well as going to larger R. So R equals 0.6 in kind of this central region. Okay, I didn't focus too much on this, but beyond the inclusive yield suppression, you'll have to trust me that well, we can flip back and forth. Turns out that as I increase my aperture size, we actually see increased suppression for larger R, which is telling us that jets are actually narrower in the QGP. We're more likely to see them if they're narrow. And you'll see this trend, at least in the inclusive case, continue to arise. We can talk about this more later. Please just feel free to ask. So, okay, so we have this kind of picture of inclusive jets, but as I said, there can be other ways to kind of exploit to understand this overall behavior. So I wanted to highlight a few. Namely, we can actually tag the structure of these jets. So for example, looking for heavy flavor jets, B jets, or photon tag jets. So I look for a photon and then I look for the recoil population, which allows us to isolate, for example, effects from mass dependence in green here. And by using these photon tagged, it can allow us to isolate color charge dependence, which is to say, highlight preferentially selecting quarks as opposed to gluon jets, which dominate in this lower PT region at the LHC. And so if you look closely here, if we compare this B jet measurement from Atlas in the green versus the inclusive case here, which is shown in the open green circles, which is, as I said, gluon dominated, we see already say at least a hint of a hierarchy here, namely that our heavy quarks are losing less energy due to these mass effects, the so-called dead cone effect. And this is not our only piece of evidence. This hierarchy picture seems to be getting stronger and stronger. We can also look at this in terms of, again, now I've switched R, so I need to switch which reference I'm looking at. So now you just look at the open black points as your gluon dominated inclusive compared to this quark enhanced in pink. And again, we see if I compare my quark enhanced versus my gluon enhanced, where my gluons are going to couple more strongly, they're broader due to the difference in my coupling factors, but also they tend to just be broader jets. They could be resolved as multiple sources. We see that they're more strongly enhanced. So we can really kind of put together some sort of hierarchy here in terms of more suppression for our gluon jets versus our B-tagged, and also versus our quark enhanced samples. So we can kind of at a broad level really talk about these energy loss expectations, and we see these kind of clear trends in suppression. However, right, so this is all very good. This is giving us a broad picture of these interactions. But now if I want to be able to go into more detail into how do I really characterize the structure and dynamics of the quark-gluon plasma, I need to start looking inside my jets. So now I'm going to turn my attention to beyond just this energy redistribution, looking into really modifications of the structure as well as jet deflection. So we're going to come back to our picture here. Again, we've seen this before. And I'm going to turn it on its side so that we can really focus on the showering of one of these outgoing high momentum transfer partons. And so if I do that, I'm going to switch this cartoon from a different colleague, which I think does a nice job of illustrating this full parton shower, and will let us think about what we're trying to probe. In particular, yeah, as I said, this kind of gives us an orthogonal domain to how we actually want to access these jet medium interactions. And there are kind of three traditional approaches, or three classes of observables that we can think about here. You group them in many different ways, but I think this is useful. So one is I would describe as in terms of kind of traditional substructure observables. So things like a jet shape or a fragmentation function, this hadron and jet measurement, where I record the fraction of momentum that's is carried by my different hadrons. So these are broadly very useful. We also have these so-called groomed substructure observables, where I try and go back and reconstruct that parton shower picture that I just showed you, experimentally, for example, and isolate my highest momentum transfer interactions in my jet, as well as a newer one on the block, let's say these so-called energy correlators, where I construct kind of flux correlations between different particles in my jet that has nice connections to kind of the underlying quantum field theory. So for today, although these traditional substructure observables are fantastic and carry a tremendous amount of information, it can be quite precise. I'm going to focus today on these other two classes of observables because they have the benefit that they can be often interpreted much more directly in terms of microscopic structure. So from an experimental perspective, I really can try and look into the structure and perhaps come up with a direct interpretation as opposed to just an overall observation of kind of modified interactions without being able to point to particular properties of the quark-gluon plasma. So so at a very high level, what we're going to try and do, I'll focus first on this groomed jet substructure, is I'm going to experimentally find a way to reconstruct the dynamics here of how my parton evolved, or at least some what we think is a reasonable approximation of this. Certainly in PP and AA, we think is reasonable, namely using this angular ordered approach. And then I'm going to unwind So I first cluster them together, going from right to left, and then I'm going to unwind these interactions going left to right. So I have some sort of tree that I construct, and I'm going to search for through each of my splittings for particular properties to reconstruct this parton shower history. And a useful way to think about this in terms of the so-called Loon jet plane, where you tend to have an angle on this x-axis and some sort of momentum scale. For example, here the KT, so this is the relative transverse momentum in the splitting example that I just showed you here. And what's particularly useful about this is we can use this to kind of map this history of my interactions in a understandable way. So the intuition that you should kind of pick up in this is one that having the quark-gluon plasma is going to set up some timescales that are relevant here in terms of the evolution. So up above this line are interactions that are occurring inside the quark-gluon plasma, whereas outside these are below are outside. And then, excuse me, we could also think in terms of angular scales that we may be able to resolve, which I'll talk about a little more in a moment. But the intuition you should have here is on the right tends to be small splitting angles, whereas the left is much wider ones. Now, how do we actually go about, what are we actually going to look for? Well, I want to be able to isolate kind of my highest momentum interactions because this should be where we expect to see the strongest modification in AA versus PP. So instead of trying to characterize my entire splitting tree, I'm going to focus on finding the hard interaction. And there are two algorithms we use to do this. So one is the so-called soft drop, which if I look at this in terms of my Lune plane here, I've just recreated my cartoon, it amounts to a kind of diagonal cut requiring me to find my first splitting that is in this region of my phase space of my Lune plane. Now, there's another way we can go about doing this. There's a little bit newer approach called dynamical grooming, which instead of just having a specific cutoff in my splitting tree, the second I find any splitting which characterizes which passes my grooming condition, I instead have this kappa metric where I can tune this alpha parameter to focus most on the splittings that I might be interested in, the dynamics they're most sensitive to. So I will instead follow my full splitting tree through, and I will select the splitting that maximizes this criteria. Now, there are a few different versions of this, right? But the one that I will focus on today, or let's discuss a little bit, is this A equals 1, which is sometimes described as dynamical KT, namely trying to maximize the splittings in this direction, the y-axis, which is going to be proportional basically to my highest KT splitting. You'll see why this is important later. There are other dynamics we can do here. Let's discuss them later. Now, in practice, experimentally, this turns out to be quite a difficult measurement to make, which means you need to impose a minimum KT requirement. This is, I'll talk about this result more in a moment, but this was quite an important discovery we've made, which means that we've been able to enable us to make these measurements, but has unfortunately some consequences in terms of what we're able to measure. Now, okay, I want to put this together just very explicitly for a moment. So if we put together all these different pieces, we have this splitting tree that I've talked about. It's going to be constructed with angular ordering, which means that my earliest splittings are going to be broadest. I can map this into my Lune plane here, where I'm going from kind of early to late on the left to later splits on the right. And I can even assign kind of some numbers and ask which methods my splittings can select. It's maybe more for intuition here, but in this case, for my dynamical grooming, I'm going to search through all these set of splittings, looking for my highest KT. So I'm going to select this first splitting. Whereas if I look at for example, something like soft drop, right, I'm with z cut of 0.2, I'm going to focus on the z value, which means I'm going to skip over this first splitting, move to this second one. And so, okay, I've constructed this example by hand to kind of highlight these points, but you can also tune your other grooming parameters to preferentially select different splittings based on kind of what you're interested in. Okay, so with that in hand, what do these actually look like in terms of measurements? So Here I focus first on the so-called RG. So I'm looking at the size of the splitting angle that I resolve in my hard splitting. And again, with the idea of isolating the impact of the medium on my parton shower. And there's been a few nice measurements of this, but I'll focus here on this one from Atlas from a couple of years ago, because I think it shows a very clear trend in terms of what jets we actually observe. So here this shows, okay, the black is inclusive, but it also has broken out, constructing its RAA as a function of what angle it resolves in what angle it measures in these identified hard splittings by soft drop. And what we see here is reinforcing exactly this point, this picture that I talked about with the inclusive suppression, namely that narrow jets in blue, or narrow subjets, or narrow splittings, are much less suppressed in terms of my modification than wider ones, right? And this is something we talk about in terms of being an overall survival bias. So these narrower jets seem to be less resolved by the medium. For example, it could be an extreme case, a single emitter versus two in this very wide case. But broadly, what this means is that I'm much more likely to find these less resolved jets. They radiate less energy to smaller angles. And these wider ones, these more gluon-like ones, tend to be much more suppressed. So this is a very nice way to kind of differentially be able to see this behavior, and we see a consistent picture. I can also turn this around this other way. So here I've shown this as a function of PT, but I can also fix my PT bit and look at my RG behavior. And you see, if I compare the data here, I see a rather characteristic shape where, again, I'm seeing kind of these narrow jets are less suppressed, more wide, but I see a transition here as well, which if you look, for example, one model calculation, there are a number of others, all suggest that this may be some sort of coherence angle. So the angle at which the medium is actually able to resolve these splittings. So this story isn't quite over yet, but we're really starting to get to the point where this seems to be something we can actually resolve. So we're really starting to get to, again, these kind of microscopic structure. What can the medium actually see of my probe? Now, one question though is that with this survival bias, what are we actually missing in terms of my jets? So there's been a very nice measurement following up on this from CMS. Again, looking at this RG, so the angle that I identify in my splitting, but now taking advantage of this through a gamma tag, right? And so I already mentioned before, this is going to bias our population towards quark-like jets. But in particular, if I normalize my selections based on my photon momentum, at least I'm going to get closer, since it's a colorless object, to my initial interaction energy, which means that instead of just selecting on my PT, I can then try and select on the so-called XJ gamma, basically the ratio of my jet PT to my photon. And so I can look for preferentially less quenched or preferentially more quenched jets, at least as the leading order picture. The next leading order picture gets more complicated, but we can still already see kind of the trends here. So in this, on the right here, in the less quenched case, what we see is, again, kind of this narrowing picture. So here they're showing the relative modification. So I've taken kind of my average RAA, normalized this out, and put it at 1. And sort of the absolute modification in the previous slide, but the picture is still the same in that I'm more likely to find my narrow jets and less likely to find my broader jets. However, if I then open up this XJ gamma to include a larger part of the population, what I'm starting to see is precisely this recovery. Now I'm seeing that at large angles, excuse me, at large angles, I'm starting to recover these jets, and I'm seeing more of a kind of flat modification as a function of my RG. Now, there's still a substantial population below this 0.4 range that experimentally is very difficult to access. So this is something that we're kind of continuing to try and access and understand experimentally. But it already shows you very nicely that if we find the right tools, we really can expand the area which the information that we extract. So there's some expectation that, again, this should still be sensitive to this color coherence picture, but we need to disentangle these effects between color coherence and, for example, the narrowing in the last slide, which is then a critical role played by models. I'm going to skip over this for now, and we'll come back to it in terms of kind of this Bayesian inference question. But what we'll take away is that there's kind of no consistent model description here. Okay, so this is one way we can try and access the structure of the medium, but I want to highlight another approach, which I find particularly, I think, intuitive in terms of trying to understand what the structure, the microscopic structure of the QGP looks like. And we can really go all the way back to the Rutherford scattering experiment, right, where I have an alpha beam irradiating on a gold foil. This was used to, right, and most of the time, it only has kind of small angle interactions, but we have an occasional scatter to large angles, which we can use as evidence for our nuclei inside of our atoms. So I want to try and use this same principle, but instead I would like to kind of shoot a quark beam into my medium and look for these occasional large angle scatters as some sort of evidence of scattering centers in my medium. So to make this a little bit more explicit in terms of what we mean from a physics perspective, so I can construct kind of a schematic, a cartoon of my probability distribution as a function of my relative transverse momentum. So how hard of a kick do I get in having some set of interactions? And our expectations here is that I should have some sort of broadening term, which is going to go as a Gaussian. So these are just kind of your soft interactions between your probe and your medium. I give you some broadening that kind of corresponds with this, these emissions to kind of broader angles. But then if you have some sort of single hard scattering term, like your Rutherford scattering to large angles, this will go with some sort of power law. So if I can access this large KT region, I can try and get to a region that's kind of preferentially dominated by these single hard scatterings, and it would indicate some sort of presence of scattering centers in my medium. So from kind of maybe a overly simplified cartoon picture, the idea is I'm again going to look through my splitting tree, and I'm going to look for interactions between one of my subjects. So I've had my splitting, and if it preferentially interacts with one of these, some sort of QGP quasi-particle excitation, some sort of scattering center, this can preferentially increase my KT. And so what I want to do then is look for a relative increase in the transverse momentum of the QGP in AA compared to PP to try and look for this type of signature, which is something we haven't seen experimentally. So okay, so we can actually try and I've done this exercise, lived this analysis within Elise, and the expectation you should set here is I'm going to again look at this kind of relative modification. So in AA over PP, so the expectation is that you see kind of some sort of clear signal of this quasi-particle scattering, I should see some sort of excess in my high KT region. Okay, and we can fill in our data here, and we actually see quite a different picture. So instead, we see this enhancement at low KT and a suppression for the data here in black at high KT, and this is kind of quite clear. So instead, what we see is that even though we're kind of searching towards this rare process, we're still dominated by these kind of overall inclusive selection bias that I've talked about so far. So in the phase space that we can measure, this R equals 0.2, kind of usual at least kinematics, we see that we kind of don't see something at least that corresponds with our naive expectation. Now, I mentioned this. The label's incorrect here, but so this is in terms of the soft drop with z cut of 0.2, but we also looked at exploring additional approaches, namely using this dynamical grooming approach. And what we see, unfortunately, is that although this concept is very nice, trying to tailor my grooming method to preferentially access data that the types of splitting I'm interested in, what we see is that the experimental consequences of this, namely being able to measure it, cuts into kind of our low KT range here. And then it's this method still seems to see somehow much more susceptible to background effects. This is dominating our systematic uncertainties here. We see kind of still hints of the same sort of suppression, but unfortunately somehow, a less precise picture. So, we have our first measurements here with dynamical grooming and AA, but we'll have to kind of go back to the drawing board to see if there's ways that we can make this more effective. Now, okay, however, since we have the soft drop picture, let's at least think about this, because this does at least present an interesting picture, right? So what's going on here? Is this somehow, can we just not resolve the quasi-particles at all in our medium? Provocatively, we could even ask, is there somehow no QGP quasi-particle structure? How do we reconcile that with the last picture that I presented earlier? Or, kind of, are we in the wrong kinematic regime, right? We can ask all these kind of questions. And one way you can go about doing this is by trying to take a look into these theoretical models, right? And so if we look here on the right, there's a number of comparisons here from so the so-called hybrid model based on this ADS-CFT approach. We have a calculation from the Jetscape collaboration, as well as from Joule, all kind of common Monte Carlos in our field, and we see fairly different predictions in terms of kind of the range here. Which, okay, if you go back to our theta G case, our RG case, the models tend to do a little bit better in terms of how they're able to actually describe the observables. There's less differentiation between them. However, what I want to note here is that we see kind of an interesting trend. Namely, if I compare this red curve here to which is the hybrid model, including Moliere scattering, this quasi-particle scattering, which we can see seems to suggest there's actually an effect compared to the purple. So this difference here from the hybrid is exactly due to this Moliere scattering term. So it's telling us that in their case you have this kind of narrowing effect, but then this scattering kicks it back up at relatively up at high KT. But then we can also talk about this Jetscape curve here, which seems to do fairly well in the data. Both of these include quasi-particle scattering. So what this is telling us is that somehow kind of our models are really giving us kind of including the same physics, or at least something close to the same physics, are giving us rather different answers. Now, from my experimental perspective, I would actually say this is, of course, very good, because it means we can start to actually differentiate what mechanisms are critical and how do we tune our models. Now, I also would be remiss here to note there's also a very nice measurement from CMS that just came out that looks at the same sort of measurement, but looking at much higher PT, much higher KT. And they also see kind of a mixed picture in terms of their model descriptions. So this is really going to give us a chance to perhaps access and start to kind of differentiate what's going on here, even at the level of our precision here by looking deeply at our models.
How much further up can they go?
Yeah, sorry, go ahead.
How much further up can they go? You said they can go to higher KT?
So they're looking at 10 to 40 GeV in KT, which is great, but the trade-off is that they're at 200 GeV jets and above. And so kind of the intuition, I maybe glossed over this, is that for kind of the size of these effects, I think kind of being in this lower jet PT region, it is potentially very helpful, right? If the kicks aren't very strong, maybe this picture of really going to very large angles is perhaps a little bit too ambitious. So if the kicks aren't so large, you kind of have a optimization problem, and if you go to high enough PT, the impacts of energy loss may not be quite so clear to be able to see. So it's of course difficult, though. If I go to lower jet PT, it also limits the KT range, right? I'm running into kinematic constraints, and okay, actually here in this case, limitations of the PP data, interestingly, not the lit light. So the CMS measurement, is kind of as I said, above 200 GeV. It's very nice, but I think you're going to be dominated by kind of vacuum-like splittings there. But okay, it was kind of they just had preliminary on this, a month or two ago. It was only compared to hybrid so far, and so there's much more that we can kind of do to interpret this going forward. But I'm very excited to see what comes of it. Thanks. Okay, so I really wanted to kind of focus on this scrimjet substructure. I'm unfortunately a little bit behind on time here, but I wanted to say just a word on energy correlators since they're of really extremely high interest in the field at the moment. So this idea here is that I'm going to again try and kind of correlate the structure, but you have this nice connection to your kind of quantum field theory in terms of thinking about correlating kind of flux in different directions, for example, in your jet or in your event, which we can then we can construct experimentally by looking at angular correlations between all of the hadrons, for example, in my observable, and constructing this in an appropriate way. So there are nice measurements from CMS as of last year, and then Elise just came out with new measurements for our quark matter. I won't say too much about these for the sake of time, except to again say we seem to really see some sensitivity to our models here. But I think as we've thought more about this further, this should really be accessing the same sort of physics. The energy correlator picture is, quite complicated, as is the substructure one. So I think we're accessing, these are kind of different views to the same sort of physics, and we'll kind of form a complementary approach as we go forward between our energy correlators and our kind of, for example, Groom substructure. So not more to say here than to say keep an eye on this spaces going forward, and I linked to some of the nice overviews from quark matter on this. So, okay, I want to get to this Bayesian inference question. So I've said some about these models now. We looked at this for the KT. I haven't shown this yet, but you can also kind of do the same exercise for the RAA, for example, for my jets, right? The point is that the kind of picture from model calculations is unclear, and even experimentally, despite our best efforts, not everything kind of has a clear, obvious interpretation just from the experimental side. So we can ask, how can we actually kind of learn from this? And I've shown you just a few of measurements, but there is a whole wealth of data from Rick and LHC. Need to update this survey. It's a couple of years old now, and even more measurements have exploded since then. So how do we do this? And we can ask really, can we make a consistent picture at all? And if we can, what physics can we learn from it? And if we actually learn from this physics, we can ask questions about, for example, what observables are most important to measure? What kind of information do they carry? And the answer to this, I would say, is via the so-called approach of Bayesian inference. It's really a rigorous way to connect our models and our data. And so the question here is basically, for a given model, which parameters are most compatible with our experimental data? So we can relate this through Bayes' theorem, where we have our data X and our parameters theta. And we have these three terms here. Our prior distribution, which is really a way to make our choices explicit about what parameters we're actually going to allow. We have our likelihood term here in the middle, which describes how well our data is described for any given set of parameters. And this is kind of a catch-all term in some sense that describes, that can capture things like covariance between my uncertainty sources and my experimental data, also possible theoretical uncertainties, so all these different pieces. And then if I combine these together in the appropriate way and able to calculate it, I can then extract my posterior distribution and on the left, which really gives us a kind of a probability of our parameters. What is our most kind of probable value given the data that we have? And so this posterior is going to kind of encode everything that we want to learn. So there are three pieces to this, namely our kind of our actual analysis steps, but also our model and our data. But if I, again, kind of put these together correctly, it's really a broad tool, not just to kind of extract these parameters, although that's certainly an important goal, but really can be used as a tool to kind of explore questions of sensitivity or of consistency between model and data, and highlight regions that, for example, our models actually maybe aren't doing very well. So, okay, unfortunately, I'm running out of time here a little bit, so I'm going to move a little bit quickly because I want to get to a few points, but again, feel free to ask questions as we either go or now or at the end. So in terms of kind of analysis, the questions that you really want to kind of focus on here are thinking about this so-called parameterization. So I need some way to externally control my model by some set of parameters. And then I'm going to, again, have to after I have this implemented, I'm going to explore kind of my parameter space. So like this picture on the right, for some set of parameters A and C, I need to look over my entire parameter space, which is quite computationally expensive to do. So the analysis I'll present today used on the order of 10 million core hours to kind of calculate just selected points in this overall phase space. And then we employ a variety of machine learning methods, transfer learning methods, active learning, as well as kind of more traditional things like Gaussian processes to be able to cover this overall parameter space. But the bottom line is that kind of these choices, for example, about my parameterization, my prior really matter. You should keep these in mind as you're evaluating what you're doing. Then you need to make some model choices. You can kind of pick your favorite Monte Carlo. There's a whole collection of these, but I just need to have something that I can calculate over my phase space. And we'll look for, and in general, for what I'll survey at least, we'll focus on this so-called jet transport coefficient Q hat, which is often used to characterize energy loss in QCD matter, and basically will tell you how much transverse momentum you pick up as you propagate through some unit length of your QCD matter. Finally, I need to decide what data I'm actually going to put in, and from here, as an experimentalist particularly, I would argue for taking a systematic approach. So here I show kind of one possible taxonomy of how I can relate really a whole collection of experimental measurements, where each line connecting through here kind of adds one experimental element. And so the idea here that I would kind of focus on is really just that your data choices really matter, but your overall goal should always be to include all available data for whatever class of observable you choose to include. You can then go back afterwards and do differential studies, picking and choosing your data. But if we choose to neglect kind of one experiment versus another without very clear reason to do so, this can kind of get us into corners of phase space which we may not want to be in. So I think kind of this general point is quite important, as well as how we treat our uncertainties, but unfortunately I'm not going to have time to talk about that today. So just to put this picture in perspective here, kind of, right, we take our data and model, combine this together in an appropriate way for analysis, and this really can extract physics in kind of a rigorous manner, as well as provide feedback on what we should be doing next. This has become quite an industry applying Bayesian inference, let's say in heavy ion collisions in recent years. I showed just kind of a selection of all kinds of things. Wonderful analyses. I highlighted at least these in the hard sector at a talk at Hard Probes. I've linked elsewhere in the slides. But there's too much for me to cover today. So I'm just going to focus on one analysis I was involved in, namely looking at inclusive jet and hadron data. Basically, as I said, kind of our goal here is we're going to include absolutely everything. So I list here what we included, and this really is kind of all-inclusive hadron and jet measurements from RIC and LHC, -1, which we had to exclude because of you have to make a cutoff at some point, let's say, given the size of these computations. So nonetheless, in total, we had measurements still from that kind of that system in terms of squared S, excuse me, and end up with 729 data points total. For this discussion, we employed this Jetscape multi-stage model, so using matter plus LBT with our choice of Q hat parameterization, kind of going down to this two-term Q hat, one focusing on this HCL-inspired parameterization, as well as then a virtuality-dependent term, which accounts for something, excuse me, like a color coherence effect, reducing interactions at kind of high Q squared. Yeah, so then doing so, unfortunately, I don't have time to say more here, but the bottom line is that we have these 6 total parameters that we can vary, that we vary in our Bayesian inference analysis. And in doing so, we then run some substantial statistics. We, as I said, use our computational techniques, and we do all this with a calibrated 2+1D hydro. So we focus on the hard sector and leave the soft sector to kind of existing calibrations. So here I focus on this kind of as a proof of concept. How do we do this as one single model? And we can, extract physics, but ideally you want to have kind of a comprehensive model comparison, right? Put a picture together to kind of disentangle that experimental and model comparison that I showed earlier. So this is our next step, but we're we need to systematically get there. So in terms of how this looks, I'm going to go from my prior distributions. I run my calculations. I compare it to a subset of my data here just for the figure. I run my analysis, and I end up with a fairly tightly constrained posterior distribution in the blue here. So this is all of these comparisons of 729 data points. You'll have to take my word for it, but in general, we see quite reasonable overall agreement. Although there are certainly some regions of tension, which I'll get to in a moment for how we can try and explore. Okay, I'm just going to skip over the perimeter posterior distribution here. Come back to this if you'd like to discuss kind of what comes out of this. But if I put all these pieces together, and I'm confident that my model at least describes my data reasonably well, I can then extract a overall kind of Q hat parameterization, or my Q hat from my data. This is what we see here on the right. This is the first kind of comprehensive extraction, including both hadrons and jets. So what's particularly key here is that we actually see that there is, even when I put everything together, we can extract a consistent Q hat. Yeah. So this is already very good, but then we want to look in some more detail. And so we repeated these calibrations using only hadron measurements in this orange and only jet in this blue. And what we see is, okay, overall, these distributions are still consistent as a function of temperature here, but it starts to be some sort of hint that Q hat kind of depends on our probe. This is quite unexpected, right? Q hat is expected to be a observable independent parameter. So how can we understand this? Well, for kind of simplicity, we're going to take a fixed slice in terms of temperature, as well as our parton energy. Right? Very explicitly, we see, they're all, there is some region of compatibility, but indeed, we kind of seem to see most preferred values are certainly a bit separated here. So how we can understand this is by going back and kind of looking at our data, namely our most precise experimental data. If we look at, for example, our charged hadrons, comparing our posterior at the LHC, we see it does fairly well in this low PT region, but as I go to high PT for my full calibration, start to see some tension between our posterior data. Now, if I kind of decide to focus more on this high PT region and redo my calibration, what I actually see is that my posterior tends to do much better in terms of describing my high PT data at the expense of kind of trading on this very low PT data. So what's going on here is that our precision at low PT experimentally is highest in this low PT region, which means we have the smallest experimental uncertainties of this low PT. However, our theory maybe is somehow the kind of the backwards of this. We expect that our theory is kind of most uncertain in this low PT region and kind of describes our data better, or is better under control at high PT. And we can see this, in fact, by kind of scanning through these PT selections, which we've done here on the left. So my kind of all hadron case is on the right, my jet on the left. And as I scan through these increasing hadron cuts, I'm focusing more on my high PT data, and I'm getting kind of a consistent picture. So my high PT hadrons consistent with my jets. And so what it's telling you really is that, right, Bayesian inference takes your uncertainties seriously. And this is telling us, right, that our low PT data are most constraining, but we're kind of missing a theoretical uncertainty to account for the fact that our model is less certain in this region. I think this is broadly true for kind of our heavy on Monte Carlos. So the point is, this is really pointing to kind of regions for phase-space improvement in our models, as well as the importance of estimating these theoretical uncertainties. Although from my understanding, from a kind of from this perspective, this is something we really need to think about carefully. So with my maybe -1 minute left here, what I will briefly say is that we've also started looking into this question of jet substructure. So we've looked at a preliminary calibration here where I compared just my jet RA to including also my substructure. And what we see here is a couple of particular important points. We see stronger constraints. We see when we add more data that we're actually getting a more constrained posterior, which if the data were fully inconsistent, we would see potentially different values. And if the jet substructure did not carry more information, we would see, we would not see improvements in our constraints. So what we're seeing is that, for example, jet substructure really seems to carry additional information, which we can try and exploit going forward. Now, there's a little bit of a tension between what's included, for example, in our fragmentation functions and this kind of separation and seeing, a consistency from a substructure and somewhat less in our kind of inclusive case. So this is under further investigation, but it really already points to, both the importance of adding these new observables, but also the potential to kind of explore even further beyond what I've shown and really disentangle the dependence here. Okay, so with that, maybe I will just leave my summary slide up here since I'm out of time. But these jets really gives us kind of these very effective tools to start really peering into the structure of the medium in terms of kind of what we want to outlook here. We had this high statistics run-through data from LHC and new data from Rick from S Phoenix and STAR go into high PT. This will really open up, I think, our ability to do precision physics. We need to calibrate kind of under the same model. So I've shown you Jetscape, but we're already working now on trying to look at this in a apples-to-apples comparison to be able to really make deeper statements about the structure of our medium and what we can extract, as well as, but as I've highlighted, we have important questions we need to think about as we develop these approaches. So with that, I'll close. Thank you very much, and I'm very happy for any questions.
Yes, thanks for the talk. Questions?
Maybe you did say it and I just missed it. But when we talk about the abstract notion of splittings in our jet, what kind of processes is that exactly referring to? Is it referring to to specific processes like decays that happen, or I'm just not exactly sure what a splitting actually refers to?
Yeah, sorry, that's a very good question. I maybe glossed over this a little bit too much. So what this means, what I really mean is that, right, even in vacuum, if I have a parton, propagating, I'm going to expect to have kind of, emissions as I shed virtuality, as I evolve and move towards kind of this point of hadronization. So this is some sort of, QCD process, a 1 to 2 type process. I also am going to have in medium, I'm also going to have interactions between my jet and my medium. Which again can kind of introduce a 2 to 2 type scattering from kind of a theory perspective. So I'm talking about either radiative or kind of collisional processes that will result from my parton showering as I said, sheds virtuality. Now this is, I think, the theory picture you can construct. Experimentally, we don't have any direct kind of a priori access to this type of information, right? Experimentally, I just record my final state hadrons. So we use some reconstruction techniques where I basically combine particles together, adding their 4 vectors in an angular ordered manner, so small angles first, and adding larger and larger ones to reconstruct something that and PP seems to describe this shower pretty well, as we expect from QCD. In heavy ions, I think this ordering is maybe a little bit less, let's just say, more open in the air, but it still at least gives us kind of an experimental tool to approach it. Does that answer your question?
Yeah, very much so. Thank you.
Thanks.
Great. Other questions?
Right. So you talked about the Q hat that bias away from each other, right? Then you said
yes.
You're missing theory uncertainties. Can you turn this on its head and say, okay, how much theory uncertainty would you need to merge these things up? Right? Because coming up with theory uncertainties is, in this case, really an adventure. I would suggest. Yeah. Can you turn it around and tell the theorists what they should expect to not know?
Right. So I think you can at some kind of some overall level. So kind of pointing at these kind of figures on the right. I can I can tell you at least by kind of some fraction how much this data is kind of missing, right? Okay, there's maybe also some shape tensions here okay. Maybe my theory colleagues in Jetscape would maybe quibble about, but okay, I'm giving my talk here as an experimentalist. So I think you can kind of point to this as at least some region that we need some kind of improvement. But I think the difficulty remains, even if I tell you, it needs to adjust, my theory uncertainty needs to adjust by, cover this 20% difference. I think the question of what do you attribute that to, what do you actually implement to do that is very difficult. So there's been some kind of recent developments on even from the Bayesian side, kind of adding in a ad hoc uncertainty that you can kind of posit some overall shape for, which is again kind of an improvement. But I think the question, so for example, I mean, this calculation uses leading order Q hat. Okay, in this case, we didn't use any shadowing, any NPDF effects type effects, but even then, we also just kind of have a sharp cutoff at TC, which is common, but physically probably is not what we'd expect the physical picture to look like. So which of those is most promising to kind of implement? I don't know if we have a way to point to that type of question specifically, and that's, I think, kind of in my mind the open question. So I maybe I've just said a lot of words to agree with you, but that kind of going into that level, it's not clear to me what we could do to do that. If we could perhaps find some observables that are uniquely sensitive to particular points of these or others, perhaps that would be an approach to at least start to ask that question. But it's not so obvious to me at the moment.
Yeah, I mean, I've seen people try to talk about theory uncertainties there, and it's mostly just pain. I mean, it's mostly just honestly. We know that we're doing something wrong, but how much, we have no idea.
Right.
At least the roughly how much you ought to expect is something that you might be able to tell.
Right. Yeah. So certainly we can say that, and I mean, I don't want to undersell the difficulty of this. I fully acknowledge this is a very difficult question. I think the point here that I think was most important, or at least that we really found interesting, was that this Bayesian inference approach actually has given us a tool to point very distinctly to say, this is precisely kind of the area of issue. Now, okay, I think maybe again, my theory colleagues may have said, oh well, this was already kind of obvious in terms of this, but we can point in very specific ways in terms of where we're missing and kind of where those improvements need to be. So I think this is a new step in that direction. And what's nice about what we've done here is that everything is on disk. We have all our simulations on disk. So I flashed this taxonomy showing these observables. We focused here just on inclusive hadron and jet, but we have really hundreds and hundreds of observables on disk that we just haven't had the chance to kind of measure yet. So we can also try and go kind of more differentially and see, if we can point folks in the right direction.
Yeah, so maybe a few questions. One that especially stuck out to me, and I think this slide is really nice. The plot on the left shows it. So I really like what you're doing here, where you're saying, if I understand what you're doing, you're saying, look, if the physics is correct, then the extracted parameters should be consistent across various subsets of the data.
Right, exactly.
And then what you show, at least to my eye, very clearly is that if you look at the hadrons and you change the lower PT cutoff fairly modestly, then you're getting huge changes in what the Q hat, extracted Q hat is. So that suggests to me that the physics encapsulated in these models is not sufficient to describe the data, or is just wrong. But you seem to have a much less strong statement. So maybe, because you seem to say, oh, everything's okay. But maybe I'm misinterpreting you.
So I mean, your excuse me, um, your point is very well taken. So I think, I mean, excuse me, sorry, I'm gonna mute for 1 second here. My voice is going 1 second. Okay, let's see if that works a little bit better. Sorry. So your question is I think very fair. So I think there's kind of two ways to think about it. One is, when we really go into this differential point, you do see these tensions. I think another fair way to think about it, though, is if we go back to this kind of overall picture. Okay, we didn't go through this in so much detail, but right, again, we're constraining to 729 measured points. And there are, it's not to say that there's no regions of tension, but there is, there's pretty good agreement over much of this range. So I think, that at least is telling us in some sense that our model, can't be 100% wrong, right? And we've, kind of even just chi-bi studies, have kind of shown us we can, describe much of the data. What this, I would say, is telling us, though, is that in this low PT region, I would, okay, maybe to make a little bit of overly strong statement, I would say it really is kind of telling us that our models are not super under control. What I will say, though, is that what it's saying is that if I look at this kind of higher PT region, this and above, we get a very consistent picture at a high PT. It's just that Bayesian inference is telling us that if you include these low PT points, where again, we have this tremendous precision, this is going to drive the behavior much more than these lower precision points. So this is kind of dominating over kind of any other kind of physics we have up here. So I think, yeah, I would say I would agree. Kind of this low PT region, I think we agree that this is probably not so well described. But I think if you look at this, 30 GeV and above, I would say the model does quite well across our kind of full set of jet and hadron observables. So I mean, I wouldn't discount that as something significant. But yeah, okay. Also, but from my experimental perspective, I of course want to improve this quality of this low PT region as well, because this is we spend a lot of time trying to get the uncertainties down here, and we want to be able to take full advantage of this.
JV doesn't seem that small to me. Like I'm trying to think like what sort of uncertainties would sort of also what sort of theoretical implementations would sort of only start working from like 30 GeV. That feels really quite large. I mean, compared to say it's sort of like temperature scale or multiple times the temperature scale, or I don't know what we're comparing to, but 30 GeV seems pretty large to me.
I mean, yeah, I mean, just to be clear, I mean, so, this 30 GeV is kind of we didn't try and optimize this to kind of be, precise, right? We, wanted to see kind of the overall behavior. But what I mean about the uncertainties even then is that my experimental uncertainty at, 10 GeV versus 20 is still substantially tighter at 10. So, I think it's really just a function of the experiment is so precise, it really gives very little room for the model to kind of move around. And so if I miss at 10 GeV, which I think is, okay, we, again, my experimental mindset is I want to keep pushing down lower and lower, but we know that there must be some region where this kind of stops working, right? And maybe 10 GeV is kind of okay. We stopped at 8 to 9, and for the kind of fully inclusive calibration. So it may be even just at already kind of this 20 GeV may be pretty reasonable. This aligns fairly well with our combined calibration. And the one thing I will kind of caution on interpreting this, I think you can look at the overall trends, but trying to interpret exact agreement here is it turns out very complicated, because you have different numbers of data points and different observables. So you really have to kind of do a careful calculation. And these are all kind of self-normalized. So I mean, to be clear, I think it's but the point is missing just by a little bit in the very lowest PT region, I think can kind of show you that this is significant. And I mean, this is kind of exactly what we asked Bayesian inference to do. It takes our uncertainties seriously, right? If we did a kind of chi by eye type picture, we look at this probably and say, wow, that, does really quite well. But what this is telling us is that, this region actually is very tough.
I take your point, and I think that things that Cole and I have been thinking about that tracks very much with our experience. What would happen if you did hadron PT greater than 40 GeV, greater than 50 GeV? At some point, does the Q hat converge and settle down as a function of the PT min?
Yeah, so already kind of at this point, this 30 GeV, okay, there is a little bit of a difference in the distribution here, but again, you have to be a little bit careful about. So this is, for example, really jet only. It doesn't include any hadrons. If I did hadron in jet above 30 GeV, for example, the picture is totally consistent. So, right, basically, yeah, as you go to higher and higher, it really does settle down to kind of something that's fairly consistent in this region. It doesn't indefinitely go kind of to the left.
Oh, maybe this is important for my follow-up question. So when you say hadron PT greater than 10 GeV, for example, I interpret that as you're comparing to the charged hadron and or pion specific data with the PT range restricted to being above 10 GeV.
Yes, yeah, for this one, for example. Yes.
Yeah, so then you should be able to do hadron PT greater than 40 GeV, greater than 50 GeV.
Right.
Jets wouldn't be in there at all, right?
Right. Sorry. Yes. So maybe my words were a little confusing. So yeah. So just to be very clear, so this orange hadron only is using all the hadron observables, no jets. This jet is using all the jet observables, no hadrons. And then this hadron PT greater than 10 is a subset of this hadron just using only above 10, 20, and 30. And so, right. So if I went on to 40, I would see it's quite consistent with this gray, 50, et cetera. It's going to stop here. It's not going to keep going.
So you've looked at that.
Yeah. I mean, so we, chose these, let's say, judiciously to kind of illustrate our point. Yeah, if you keep going higher, it's the jet and hadron picture is fully consistent.
And then when or have you made any statements about whether the data is consistent across experiments? I'm thinking especially, say, Atlas and CMS charged hadron out at very high PT.
Yes, very good question. So I didn't say anything about this here, but we have thought about this. And so there are a couple answers to this. So one, indeed, I would agree that there seems to be some differences between the Atlas and CMS at high PT, both in the jet as well as in the charged hadrons. So the difficulty with this paper here is that unfortunately the Atlas charged hadrons at 5 TeV, which is kind of their most precise comparison, came out after we did these calculations. So so we unfortunately don't have that included in this paper, but we have all of our kind of raw data on disks, and we're actually currently doing a reanalysis of this and adding some other observables. So we will be able to say more on this soon, hopefully. In the meantime, though, but we included both the jets from Atlas and CMS. Let's see if I can find these quickly. Maybe not. I might have put actually, that might be in my backup. Let me see if I can find it quickly. But also, yeah, so this is also true. Do I focus on these are all relatively low PT, but okay, but already, yeah, okay, you'd have to use the CMS, but so you can already kind of see the point there here. So this is the Atlas 5 TeV, R equals 0.4. The CMS tends to go more kind of here at higher PT. So our posterior is a little bit more consistent with the CMS. So we investigated this question precisely, and so what we did, I think I forgot to include the figure here. Apologies, but it's in our paper. We did a calibration where we actually just cut at 100 GeV for all observables. So basically the concept was, if I just exclude this region where we have this disagreement, and okay, we did this many differential ways, we just reported the 100 GeV one, what does it do to our calibration? And the answer is nothing. And the reason why it makes so little impact is precisely because of these uncertainty arguments. The uncertainties in this kind of high PT region are so large relative to this kind of low PT region that even if we have a disagreement here, it really will not make an impact. You'll increase kind of your overall chi-squared effectively, but it really won't, it won't shift your posterior much. Now, that's not a very satisfying answer, I think, at some level. So other things that we've talked about, though, not yet implemented, but thinking about is, for example, you could imagine constructing a likelihood where instead of just taking the distance between kind of the posterior both between the atlas and the CMS, you could construct a posterior where it's minimized more when you're close to one or the other, and see if there's a preferential posterior for those two. What my expectation kind of continues to be, the uncertainties are large enough that it's unlikely to kind of make a strong impact, but it will be very interesting to see what happens with the hadrons when we include the atlas ones as well, and see if because that, at least that kind of discrepancy starts to, at least the hint to my eye, starts much lower in PT. So at least when you're kind of in a higher precision region. This is something I would say that kind of as you know, having experimentalists in Jetscape, we often prod each other also about trying to resolve these questions. Experimentally, I don't know if there's going to be a lot of movement until folks really get new precision measurements out with the Run3 data. So it still may be kind of a couple of years time scale before, or maybe sooner than that, but to kind of give a stronger answer on this. You also can, something that we haven't tackled yet, but also relevant to this question, is actually this RAA double ratio, comparing Atlas versus Elise. So we unfortunately won't be able to comment on this directly because the Atlas is an RCP as opposed to an RAA, and due to kind of model choice, how the modeling is done, Jetscape can't do peripheral jet quenching. We just kind of are missing too much important physics to, let's say, for our theory friends to let us make these comparisons. But you also have questions like this. So Bayesian inference, I think, gives you a tool to kind of try and think about these questions. As I said, constructing your likelihood in different ways, what have you. But I think this is really very much an open question in terms of how exactly we resolve all of these things.
It seems interesting if you go back to that almost last slide with the Atlas and CMS jet data.
Yeah.
In some sense, it seems consistent where in the charged hadrons, Atlas is well below CMS, and it seems like the jets, it has the same story, and it makes me wonder if there's some kind of systematic experimental issue that we're seeing manifested here.
Right. So it is possible. I will say, okay, I was hoping to say a little bit more about our air treatments here, but okay, I got maybe carried away with the physics on this. But we do, as part of the analysis, we do account for shared kind of correlated uncertainties where we can. We don't have okay, we count for some of the experimental kind of wide uncertainties, but not maybe all of them yet, because again, kind of some of these are detailed questions of how well can I model this year over year, and how well can I describe those correlations. But I agree with you. Kind of, if I look at this by eye, it seems there may be a little bit of kind of systematic offset. So I think this is certainly something that we are interested in kind of trying to look at further. But I suspect that kind of the hadron question will be more fruitful than the jet one, just because the region of disagreement is right. Where you see this from the CMS, it's just relatively small, right? This is the 2.76, but the 5 TeV is only a few kind of high PT points. So, yeah, but I think you're right on. I think this is a question that is important, and we need to be able to shed better light on. And it's going to have to be both from both theory and experiment, I think. Experiment certainly needs to be able to kind of make some better statements about this, but I think theory can, also help us start to disentangle this.
Super, thank you.
Thanks.
Other questions? Okay, well, I've got a question. So I'm kind of curious. So it seems like in this Bayesian analysis approach, this sort of concept, which maybe is a bit older from like more frequentist chi-squared type studies, which people would report things like p-values, is sort of no longer there. I mean, it seems like the Bayesian analysis sort of tells you, given that this theory is 100% true, this is the most likely parameter set. Do you guys think about this sort of, I mean, what's the prior for like this theory is just wrong? I mean, it seems like, like if you're missing the low PT, you're probably like many standard deviations away from it. I mean, presumably if you were to calculate something like a p-value, it would be close to 0. And yeah, I'm kind of curious what you think about that.
Yeah, so I mean, indeed, this statement is only kind of valid in terms of kind of the model, and we take, I take what my model gives out, and right, it asks how consistent, which parameters are most compatible with my experimental data, right? It doesn't necessarily say that kind of my model is correct. There are ways that you can address this. So, for example, there's these concepts of Bayesian evidence. This is related to this bottom term, but also kind of things, this so-called sorry, I lost my words here, but right, there are tools in Bayesian inference you can use to, for example, say I did Jetscape and I did some other model in a kind of apples to apples way. I actually can, there are measures I can come out with for what model kind of better describes the data that I have available. I think we know for a fact that none of these models are going to be fully correct. None of them have all the physics that we expect to be there. Even just up to next to leading order Q out formulations are not a small correction to leading order ones, right? I think the benefit here really in the Bayesian approach is around actually this prior distribution. So for this analysis, we used a flat prior, but something that we're actively exploring is the impact of using kind of informative or non-flat priors. And so I think one of the things you're kind of missing in the frequentist approach is just explicitly what kind of an explicit statement of kind of what you're putting in. And this in fact can actually matter. So I didn't spend too much time on this, but it turns out we are getting kind of to edges of our kind of parameter phase space, and you can actually, I mean, for example, even just if you stare closely kind of at this edge and look at kind of the limits, we couldn't go much further, let's say, to the right in our analysis. You just can't kind of, for the parameters that we put in, you can't do that. And so in the Bayesian case, we at least can be very explicit about what these limitations are, whereas kind of in the frequentist case, you are I am not aware of kind of a precise way of kind of describing this and being able to kind of account for this in your model. So I've said a lot of words maybe without fully answering your question. What maybe to phrase it just as what if Jetscape is totally wrong? I don't think anyone's saying it's totally right, but at least so these statements need to be taken within the context of the model. But if, for example, if our kind of model description was totally incoherent, for example, okay, we didn't plot the prior in this case, but for example, if none of this was informative, it was just all over the place, you would see, for example, that I just don't get any meaningful constraints on my prior distribution, right? It's all just a mess. So I think that's at least telling us that we're not, that there's something that we can extract here and try and understand, even if our model description is not perfect.
So I guess you're saying it's sort of, you can only really compare things relative to each other, and if you wanted, you could expand your Bayesian analysis to include more models, and then you'd be able to say something meaningful about the difference in their ability to describe the data. Okay.
Yeah, exactly. Yeah, that's a nice way to summarize it. And yeah, I mean, this for me is kind of my highest priority question is how to do this next. We've already been trying for some years to kind of get folks to come together to kind of do an apples to apples comparison, and it's very difficult, both from a physics perspective, but also from a sociological perspective. So we're going to keep trying, but yeah, it's I hope we'll make progress.
And then I just had one more question sort of related to your point about, I think you mentioned sort of the covariance matrix. And it seems like, so I mean, my memory of this paper is that there's a fair amount of modeling, at least in the covariance, so it's sort of in the systematic uncertainties. And as far as I understand, from an experimental perspective, this sort of covariance matrix for at least one analysis is something that can be computed. Like they could report the covariance matrix. I mean, maybe I'm I could be wrong about that. And then is there any sort of, within the sort of experimental community, is there any sort of driving force for them to do that? Because it seems like, I mean, like you say, there's sort of 10 or 100 million CPU hours or whatever you said being spent on. So it kind of makes sense that they should spend some more to get the covariance matrix. So it seemed like quite a big sort of modeling uncertainty in that sense to me when I read that paper. But
yeah. Okay, I don't think I have any systematic breakdowns. Okay. So your question is exactly on point. So a couple answers. So one, okay, I didn't say so much of it because of I don't think there are so many experimentalists in the audience, but we continue to ask folks to at least report signed uncertainties, because if I have the sign of the direction, so how far do I deviate in what particular direction, I can construct a covariance matrix from that. Now I am an experimentalist, and what I will say is that even for this analysis, for example, I was unable to report kind of the signed uncertainty for every source. So some of them are, you kind of run into a few different issues. One being that it's not always, if I have some kind of nominal value and I have to, kind of vary it by some percentage, it's not always obvious experimentally kind of if there is actually a clear kind of preferential direction to report my sign. Right, a lot of uncertainties end up kind of just being symmetrized, so one is kind of just a limitation in terms of how well we can understand our uncertainties. Systematics there's certainly some art to them. It's not just kind of straightforward consistent, let's say, expression to derive every single one. So that's part of the limitation, is that it's just not always clear kind of how to actually construct these. For some sources, others are much more direct. The other problem is that computationally, running one of these kind of systematic uncertainties can be as expensive as kind of running the experimental analysis in the first place. And so, I mean, for example, kind of on, let's say, this analysis on the right here, to construct all of my systematic uncertainties may mean running already kind of on the order of 20 times the CPU time that I actually need to run the analysis in the first place, which it's not millions of core hours, but it's kind of significant in terms of experimental resources. And so if I need to run this particularly even more differentially, right, because the problem is that I can the sign uncertainties are good, but they're kind of not the final word. Reporting a full correlation means I need to kind of vary my systematics in a a correlated way, which now kind of explodes my compute time. So I would say kind of the bottom line answer is that one, it's not so easy for some sources, but then number two, it is still quite a computational cost. That's not to say that I want to let experimentalists off. Every single talk that I give, I make this point about signed uncertainties. And I've reported from my own analyses, and at least some colleagues have started to do this. So I'm hopeful that we're at least starting to make progress. Now, in terms of your question about kind of how do we estimate these uncertainties and how significant, are these kind of modeling choices? In our previous paper, we kind of made some estimates of these dependencies and did some closure tests to see kind of what is more or less significant. I think this is very much a question, though, that's open in terms of how we can improve this. So there's a recent paper from Ron Soltz at Livermore, kind of doing some sort of Q-hat-like calibration here, but kind of in a simplified model, but trying to focus more on kind of how we treat these experimental uncertainties and their correlations. And we know that it's your choices are significant. He kind of shows that his collaborators show that in fact we still have some work to do in terms of how we do these things. So I would suggest you to. I don't want to butcher their conclusions, but it's definitely a paper worth reading. I think bottom line, my expectation is that we still can do better on this, but I also don't expect the overall picture to dramatically change beyond kind of what I've shown here. That's my expectation, at least.
Okay. Cool. Thanks.
Good.
More questions?
Yeah. Okay. All right.
Excellent. Thank you very much. Very much appreciate the invitation to come speak here.